Experimental study on structural health monitoring of carbon fiber reinforced concrete beam. Abstract. The main objective of this project is to monitor the structural health of carbon fiber reinforced concrete beam by using sensor embedded in it. The problem that has been identified is there is no standard method of structural health monitoring for carbon fiber reinforced structures. Carbon fiber reinforced concrete is those structures in which the steel reinforcement is replaced by carbon fiber mesh. The grade of concrete that is used is M25 with OPC53 cement. 6 mm size of coarse aggregate and manufacturing sand. Casting of prism and beam specimens is done by placing the carbon fiber mesh in box type. The carbon fiber reinforced concrete is the structure which the steel reinforced is replaced by carbon fiber mesh. In this study, the casting the prism and beam specimen is done by placing the carbon fiber mesh. The concept of design is not only to monitor strain but also act as a structural strengthening mechanism in target. The sensor that is used thermocouple, which is used for measuring the internal concrete temperature. The temperature of carbon fiber reinforced concrete beam during loading is measured. To arrive, the relation between internal concrete temperature and load applied. To monitor the structural behavior of carbon fiber reinforced concrete beam during structural health monitoring system. The temperature range can be fixed in the sensor for continuous monitoring of structure. While the system can be programmed to ring an alarm when temperature exceeds the specified limit. Keywords: carbon fiber reinforcement, structural health monitoring, thermocouple sensor, temperature. 1. Introduction. Structural health monitoring refers to process of implementing a damage detection and characterization strategy for the structures. A typical health monitoring system is composed of a network of sensors that measure the parameters relevant to the state of the structure and its environment, such as temperature, stress, delamination, strain, vibration, and humidity. To properly manage civil infrastructure, its condition, or serviceability, needs to be assessed. Many variables can be monitored and used for the assessment. Tunnels are being monitored for traffic accidents and air quality. The urgent earthquake detection and alarm system measurement and proper data processing are expected to give a reasonable assessment of serviceability can then be improved based on the assessment. Sensing physical quantities in detail offers the potential to better estimate structural conditions. For river bank protection, for instance, water level may be monitored and the associated load estimated. Precipitation rate and groundwater level are an important indicator to predict slope failure. Structural condition assessment is, however, not always straightforward, such is the case in structural health monitoring, SHM, of buildings, bridges, and towers. 1.1 Health assessment of engineered structure. The concept is widely applied to various forms of infrastructure, as countries all over the world entree into greater period of construction of various infrastructure bridges to skyscrapers. Especially when damages to structure are concerned, note that there are stages of increasing difficulty that require the knowledge of previous stages, namely A. Locating the damage. B. Quantifying the severity of the damage. C. Detecting the existence of damage on the structure. D. Identifying the types of damage. 1.2 Textile reinforcement. Textile reinforced concrete is a type of reinforced concrete in which the usual steel reinforcing bars are replaced by textile material. Materials with high tensile strength, with negligible elongation properties are reinforced with woven or non-woven fabrics. The fibers used for making the fabric are of high tenacity like jute, glass, fiber, Kevlar, polypropylene, polyamides, nylon, etc. Textile reinforced concrete is generally thinner than traditional steel. Reinforced construction is 100 to 300 mm thick. TRC is much thinner due to an extra protective layer of concrete that is not needed for its design. 2. Material properties. In this study, the following materials are used in testing of materials such as material cement, sand and coarse aggregate to determine the following properties: fineness of cement, consistency and initial setting time of cement, specific gravity, fineness modulus of fine aggregate and coarse aggregate. 2.1 Concrete materials. 2.1.1 Cement. Ordinary Portland cements, OPC, the basic Portland cement and is best suited for use in general concrete construction. It is of 3 types: 33 grade, 43 grades and 53 grades. In this study 53 grade of cement is used. Table 1 Physical properties of 53 grade ordinary Portland cement. Properties of cement values. Fineness of cement 9.2%. Specific gravity 3.12. Consistency 32%. Initial setting time 26 minutes. 2.12 Fine aggregate. According to IS 383:1970 the fine aggregate is being classified into 4 different zones, that is Zone I, Zone 2, Zone 3 and Zone 4. Manufactured sand is crushed aggregates produced from hard granite stone which is cubically shaped with grounded edges, washed and graded with consistency to be used as a substitute of river sand. Tested conducted on fine aggregate are specific gravity, fineness modulus and water absorption. Table 2 Physical properties of manufactured sand. Properties of fine aggregate values. Specific gravity 2.55. Fineness modulus 2.81. Grading zone 2.1.3 Coarse aggregate. The coarse aggregate is the strongest and the least porous component in concrete. The optimum size of coarse aggregate used for carbon fiber mesh with 5 mm grid size was found to be 20 mm and hence it was adopted. The specific gravity test, fineness modulus test and water absorption test are conducted on coarse aggregate. Table 3 Physical properties of coarse aggregate. Properties of coarse aggregate values. Specific gravity 2.55. Fineness modulus 6.71. Water absorption 1.45%. 2.1.4 Carbon fiber mesh. To improve the tensile reinforcement, high-strength fabrics made of textile reinforcement can be used. The multi-filament yarn made of carbon fiber mesh was used in study. Carbon fiber mesh was used as reinforcement and other materials. Properties are listed below. Table 4 Properties of carbon fiber mesh. Name carbon fiber mesh. 2.2 Thermocouple sensor. Thermocouple is an electrical device consisting of 2 dissimilar electrical conductors forming electrical junctions at differing temperatures. A thermocouple produces a temperature-dependent voltage as a result. The voltage generated at a single junction of 2 different types of wire is what is of interest, as this can be used to measure temperature at very high and low temperatures. The magnitude of the voltage depends on the types of wire being used. Generally, the voltage is in the microvolt range and care must be taken to obtain a usable measurement. 2.3 Concrete. 3 Experimental investigation. 3.1 Test specimen. 3 specimens of 1,200 mm x 150 mm x 200 mm were casted with thermocouple sensor embedded at the middle and 1/3 of the prism, along the transverse direction. Carbon fiber mesh placed in box-like sandwich shape having cover of 15 mm on all sides. 3.2 Experimental setup and loading. The 3 prisms were tested to failure in a 2-point loading system with a clear span of 50 mm and effective span 400 mm. The load was applied using the universal testing machine. 2 dial gauges were used to measure deflection. The testing of prism was carried out in universal testing machine of 1000 knots load capacity. The load was applied in specimen and corresponding change in temperature was noted. 3.3 Result in discussion. For the applied load, corresponding change in temperature was noted. The load change for carbon fiber reinforced concrete at 1/3 and mid distance. The relation between internal concrete temperature and applied load for specimens has been arrived as below. And for every change in load, the corresponding change in temperature has noted. Relation arrived. Conclusion from the testing: the internal load temperature of the concrete also increases, which can be used as means of warning, and it can be inferred that with increases in loading from the relation, it is known that temperature variation remains the same for various specimens of same kind. Further studies and experiment have to make different specimens in different sizes to arrive global relation between the temperature and load, thereby make health monitoring system more economical with thermocouple sensors.